Welcome to This Explainer. Today, we are going to completely decode the exact strategies you need to conquer Cambridge Mathematics word problems and equations. Okay, let's dive into this immediately, because in an exam, the clock is literally always ticking. I want you to imagine you're sitting in the exam hall right now. The invigilator says you may begin, and you flip open your paper to a massive, intimidating 6-mark question. You know that feeling, right? The blank page panic is completely real. When faced with this intense pressure, I see so many students fall into two traps. The first type of student completely overloads the answer space with raw mathematical facts and formulas with zero actual analysis. The second type? Well, they see numbers, they totally panic, they rush the calculations, and they completely miss the command word requirements. Today, we are going to transform those flaws into an absolute, unbreakable strategy.
So the absolutely crucial point here is figuring out how to break down any question and deliver the mathematical headline. Now, what's really interesting about this concept is dealing with deadline pressure. In a real exam, you don't have all day to sit around pondering the philosophical meaning of a triangle. You just don't. You have to break down the story, which is that complex, sometimes deliberately confusing word problem presented by the examiner, and immediately deliver the headline. And by headline, I mean your crystal clear, mathematically sound answer. Honestly, the difference between a passing grade and top marks isn't just knowing the math. It's about flawlessly executing a strategy when the exam clock starts ticking. In this explainer, we're going to make sure that you never overload your page without analyzing, and you never, ever rush without reading the question properly. To do that, our agenda today is packed with high-value exam techniques. First, a strategy blueprint. Second, conquering simultaneous equations. Third, the quadratic toolkit. Fourth, linear and nonlinear combinations. And finally, navigating inequalities. Let's get to work. Section 1, the strategy blueprint. Let's dive right into getting the foundation right when constructing equations.
Top students rely on a strict, no-nonsense, 3-step framework derived directly from the textbook: construct, solve, and most importantly, verify. This brilliantly illustrates exactly how you structure a perfect response. Let's look at the very first step. Construct the equation from the context. Often, the core information is hidden away within the context of a word problem or a tricky diagram. You aren't just handed the equation on a silver platter, you literally have to build it yourself. Step 2, solve the equation for the unknown. This is where your algebra skills finally get to shine. And step 3, check or verify by substituting the value back in. Guys, do you know why students so often lose marks? Because they completely skip step 3. They find a value for x, breathe a sigh of relief, and immediately move on to the next page. If you just take 30 seconds to substitute your value back into the original context, you essentially grade your own paper before the examiner even sees it. You guarantee your own marks. And hey, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the math.
So, when examiners hide an equation inside a geometry problem, you absolutely must use these ironclad rules to construct your starting formula. Look at this translation guide. Let's practice a real scenario. Imagine you're given a rectangle, and they tell you the area is 16. The base is written algebraically as x plus 3, and the height is simply 2. You can't just stare at the drawing hoping the answer appears. You have to translate that shape context into a rigid mathematical statement. We construct it like this: 2 times, open bracket, x plus 3, close bracket, equals 16. Boom, there's your equation. Then we expand the bracket to get 2x plus 6 equals 16. We subtract 6 from both sides to get 2x equals 10, and we divide by 2 to find x equals 5. But wait, remember our blueprint. We link back and verify. If x is 5, then the base is 5 plus 3, which is 8. Does 8 times the height of 2 equal an area of 16? Yes, it absolutely does. That right there is how you turn theory into guaranteed stress-free marks.
Section 2, conquering simultaneous equations. Here, we are going to look at solving for two interacting unknowns. You have two highly strategic tools at your disposal here, and choosing between elimination and substitution depends entirely on how the equations are presented to you on the page. Let's look at the left side, the elimination method. The core aim here is to completely remove one of the unknowns by either adding or subtracting the two equations vertically. You want to use this method when the coefficients, the numbers attached to x or y, are exactly the same or can easily be multiplied to be the same.
On the right, we have the substitution method. You use this when one of the equations is already arranged beautifully in the format y equals something or x equals something. You just pick up that entire algebraic expression and drop it directly into the second equation. Knowing exactly which method to choose right out of the gate is going to save you critical minutes on the exam clock. This brilliantly illustrates how simply adding two equations together perfectly eliminates the y variable, leading you straight to the answer. Let's walk through this specific example step by step, just like you would in the exam. Equation 1 is 3x plus y equals 9. Equation 2 is 5x minus y equals 7. Notice anything? Look at the plus y and the minus y. They are perfectly mirrored. So if we draw a line and add these two equations vertically together, 3x plus 5x gives us 8x. The plus y and minus y, they cancel each other out completely. They equal 0. Poof, gone. And 9 plus 7 gives us 16. Suddenly, this complex simultaneous system completely collapses into a wonderfully simple linear equation. 8x equals 16. Divide by 8 and x equals 2. But remember our blueprint, we aren't done. We take x equals 2 and substitute it right back into equation 1. 3 times 2 is 6, so 6 plus y equals 9. Subtract 6 and y equals 3. Always check both values in the second equation to be absolutely certain. Let's see. 5 times 2 is 10, minus 3 is 7. It works perfectly. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 3, the Quadratic Toolkit. Let's step up our game and explore how to handle quadratics. This core mathematical law is the exact reason why factorizing a quadratic equation actually works. Let's say you have x squared minus 3x minus 10 equals 0. I really want to let this sink in for a moment. It's called the zero product property. If I tell you right now that a times b equals 0, there is absolutely no mathematical way that can happen in the universe unless a is 0 or b is 0. Think about it. So when you factorize x squared minus 3x minus 10 into two neat little brackets, you get open bracket x minus 5 close bracket times open bracket x plus 2 close bracket equals 0. Because of this exact mathematical law, we can split this intimidating quadratic into two separate, incredibly simple linear equations. Either x minus 5 equals 0, meaning x is simply 5, or x plus 2 equals 0, meaning x is negative 2. It really is that elegant. Now, what happens when factorization isn't so obvious? You need to rely on the other two powerful methods in your toolkit. Sometimes you'll flip the page and face an equation like x squared plus 7x plus 3 equals 0. If you try to think of two whole numbers that multiply to make 3 and somehow add to make 7, well, you're going to realize pretty quickly it's impossible. The number 3 only has factors of 1 and 3, and 1 plus 3 is 4, not 7. The core takeaway here is that factorizing into brackets has completely failed us. The numbers just don't work out neatly. But when factorizing fails, we don't panic. We just select the next tool in our quadratic toolkit, which brings us to the absolute most robust weapon of them all. Enter the quadratic formula. This is your ultimate bulletproof fail-safe for finding x, provided you accurately identify your a, b, and c integers right from the start. But here's the catch. The biggest flaw students make here is completely ignoring the negative signs. Let's look at the equation x squared minus 4x minus 2 equals 0. Here, our a is 1, our b is negative 4, and our c is negative 2. Let's plug them in perfectly, nice and slow. Negative b becomes negative 4, which flips to a positive 4. Then we have plus or minus the square root of b squared, while negative 4 squared is a positive 16. Then minus 4 times a times c. That's minus 4 times 1 times negative 2, which gives us a positive 8. So under that square root symbol, we have 16 plus 8, which is 24. We divide the whole thing by 2a, which is just 2 times 1, so 2. So we have 4 plus or minus the square root of 24 all over 2. Type that carefully into your calculator, and this gives us two distinct, highly accurate decimal answers. X equals 4.45, or x equals negative 0.449. Execute the formula correctly, watch those negatives, and you secure full marks every single time. Section 4, Linear and Nonlinear Combinations. All right, take a deep breath. We have officially reached the final boss of equations. So, the absolutely crucial point here is that by using the substitution method, we combine both equations into a single quadratic that we already know how to solve. Listen, you cannot use the elimination method here. Why? Because x squared and x are not like terms. You can't just subtract an x from an x squared and expect them to magically disappear. It doesn't work. Instead, we use the profound logic of substitution. Think of it this way. If y equals expression A, and y also equals expression B, then logically expression A simply must equal expression B. By setting them completely equal to each other, we totally bypass the y variable and create a flat, horizontal plane field containing only x's.
Look at how cleanly the steps flow here. We substitute, we rearrange to collect all the terms on one side, and suddenly a really intimidating complex problem just becomes a standard everyday quadratic. Let's break down the algebra carefully. Step 1. Set them equal. 2x plus 3 equals x squared plus x minus 9. Step 2 is the rearrangement phase. We want one side to equal exactly 0 because that's the standard quadratic format we need. So let's move everything to the right. We subtract 2x from the right side. X minus 2x gives us a negative x. We subtract 3 from the right side. Negative 9 minus 3 gives us negative 12. So our brand new beautiful equation is x squared minus x minus 12 equals 0. Step 3. We factorize. We need two numbers that multiply to negative 12 and add to negative 1. Those numbers? Negative 4 and positive 3. So our brackets are x minus 4 and x plus 3 equals 0. This means our x values are 4 and negative 3. We have our x values, but are we done? No way. We need the corresponding y values. Take x equals 4 and substitute it into the easy linear equation. Y equals 2 times 4 plus 3. 8 plus 3 is 11, so coordinate 1 is 4, 11. Now for x equals negative 3. Y equals 2 times negative 3 plus 3. Negative 6 plus 3 is negative 3. Coordinate 2 is negative 3, negative 3. That right there is how you execute flawlessly under pressure.
Section 5. Navigating inequalities. Let's jump into our final critical skill. Now, linear inequalities act almost exactly like normal equations, but with one massive grade-dropping trap. If you divide or multiply both sides by a negative number, the math completely breaks down unless you flip the inequality sign. Let's analyze this split screen carefully, because this is where examiners catch people out. On the left, if you start with the undeniably true statement, 6 is less than 8, and you add 2, you get 8 is less than 10. That's still true. If you multiply by a positive 2, you get 12 is less than 16. Still totally true. But look closely at the right side. If we take 6 is less than 8, and we multiply both sides by negative 2, we get negative 12 on the left and negative 16 on the right. Ask yourself, is negative 12 less than negative 16? No, absolutely not. Negative 12 is a larger number. It's closer to 0. The mathematical statement becomes utterly false unless we forcefully reverse the inequality sign to make it negative 12 is greater than negative 16. This is the single biggest trap in navigating inequalities. Whenever you divide or multiply by a negative across an inequality, you absolutely must flip the sign. Now, when faced with a dual inequality, don't panic. Just treat it as two separate inequalities happening at the exact same time and apply your algebraic operations across the entire board. You are basically trapped in the middle, trying your best to isolate x. Look at the expression. 7 is less than 3x plus 1, which is less than or equal to 13. Your single goal is to strip away that plus 1 and that times 3 from the middle. First, let's subtract 1. But remember, whatever you do to the middle, you must do to the left boundary and the right boundary. It's a package deal. So 7 minus 1 is 6, 13 minus 1 is 12. We are left with 6 is less than 3x, which is less than or equal to 12. Next, we divide everything by a positive 3. And since it's a positive number, what do we know? Our inequality signs stay exactly where they are. 6 divided by 3 is 2, 12 divided by 3 is 4. Our final, incredibly elegant solution is 2 is less than x, which is less than or equal to 4. If you had to draw this on a number line, this is an open, empty circle at 2, drawing a line over to a solid, filled-in circle at 4. Perfect. Now that you understand the fundamental architecture of these mathematical problems, the real test begins. You have the blueprint to construct equations directly from geometric contexts. You have the toolkit to solve complex quadratics when factorization totally fails you. And you have the strict rules required to navigate tricky inequalities without falling into the examiner's negative number trap. The difference between a good grade and a truly great one isn't just knowing the math, it's having the discipline to apply these exact steps under intense deadline pressure. Knowledge is only the foundation. Execution is the key. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. So, what critical mathematical tool are you going to practice constructing first today? Keep practicing, and I'll see you in the next explainer.